Hello everyone, so this is going to be the first video, an introductory video on Riemannian geometry. So before I start the actual thing, let me tell you what is the prerequisite and what are the books that you can follow. So for the prerequisite for Riemannian geometry, it basically requires introductory topology and the smooth manifold theory. When it comes to introductory topology, we all know that the classical book is by Munkres. You can follow that, but there's another book which is called Elements of Topology by an Indian author. His name is Tej Bahadur Singh, and this is a quite good book. And even if you already have the knowledge of topology, I would highly recommend you to actually go and have a look at this book and try some exercises from this book. And when it comes to smooth manifold, that is also required to study Riemannian geometry, there is a very classic book by John M. Lee that you can follow, and there is another book by W. Loring. These are two quite good books. The book by two Loring is written is a little bit simpler language, but is still a standard textbook when it comes to smooth manifold and all. John M. Lee is a little bit difficult than the two Loring's book, but still you can study it and it will provide you quite a lot of in-depth knowledge of the smooth manifold. So that is what you require for the prerequisites of Riemannian geometry. Now, when it comes to the books for Riemannian geometry that you can follow, well, when you will look for the books, one thing that comes in your way is the knowledge of tensors. So if you are not familiar with the tensor, then you can follow this book, the book by Manfredo P. do Carmo, the book of Riemannian geometry. You can follow this book if you are not familiar with tensors. But if you are familiar with tensors, you can follow any of these books, or there are many more books on Riemannian geometry. You can follow them also. But if you are using any of these books or other books that introduces Riemannian geometry using the concept of tensors, please be careful, because the tensors, if you look at the multilinear map definitions, they are defined as the product of dual spaces and the vector spaces. And this product can be made in a different manner also. You can take vector space first and dual space later, and this will take some certain things. So have a look at that first, only then move ahead according to that. Okay, so this is the prerequisite and the books that you can follow on Riemannian geometry. So let us now start the actual thing that we are going to do here. So let's say that you have a smooth manifold. So M is a smooth manifold. So what is the structure that we have till now here? We have a set M, and since it is a smooth manifold, that means it has a topology tau. It also have a smooth structure, that is, you have provided a smooth atlas to it. This is a smooth atlas. That is what you require for a topological space to be a smooth manifold. Now note that up to here we have no structure that can provide a tool to measure length. Because you see, manifolds, very roughly speaking, it is true that manifolds are nothing but the surfaces in higher dimension. And if you have a surface, what is the first thing that you would love to do? Is the calculus. You would love to do calculus. But how are you going to do calculus if you don't even have a tool to measure length. If you can't even measure length, forget about doing any calculus on it. So that's what we are going to do first. What we are going to do is that we establish a structure. We establish a structure on a smooth manifold that allow us to measure length. But if we just wanted the length, we could have provided a norm. But we don't just want length, we want more than length. That is, we also want to be able to measure angles. So we are more special than that. So what we do, let's have a look at our Euclidean space. If you remember, in Euclidean space, to measure length and angle, the tool that we used to have was an inner product. Now you know that inner product is defined on a vector space. But in general, if you look, manifold is not a vector space. It is not necessary in the definition of a smooth manifold. It is not mentioned that it needs to be a vector space. You can have a manifold which is not a vector space, but the inner product is defined on a vector space. So what are we going to do? Have we lost all hope? Of course not. If you have studied the theory of manifolds properly, you know that for each point P belongs to M, which is the smooth manifold, you can define a vector space, a very obvious choice for vector space, and that is your TPM, the tangent space. At each point, you have this obvious choice for the vector space. So what we can do, we can construct an inner product on each of these tangent spaces, and that would allow us to have a notion, a tool to measure length and angles and all that. So that's what we are going to do. So let's formally define this thing. Let's say you have a smooth manifold. M is a smooth manifold. And P is some point on this manifold. Okay? And the tool that we are going to have, this inner product that we are going to define, this is going to be called Riemannian metric. So what this Riemannian metric does is basically to each point P, it provides a symmetric, we define a symmetric bilinear and positive definite inner product. So what is this? This is GP. I'm putting P here to emphasize that we are providing this structure to each point. We are assigning this thing to each point. So GP is what? GP is an inner product defined on the tangent space. So this is from TPM cross TPM to R. So this is a real inner product. So of course, if it is a real inner product, it is obviously symmetric. I have written symmetric here just to emphasize it, that it must be symmetric, because you know, in general, if you have an inner product defined on some field F, then it need not be symmetric. And the other thing that is we are required is bilinearity and positive definiteness. That's what we are required. And this is called the Riemannian metric. So basically what Riemannian metric does, it assigns an inner product to each tangent space TPM that you have at each point P, at the point P of the smooth manifold M. That's what Riemannian metric does. Okay. Now, if you are familiar with the tensors, then in terms of tensor, and if you are not familiar with the tensor, you can ignore this definition. But for those who are familiar with the tensor, in terms of tensor, we say that Riemannian metric is a symmetric. Again, I'm writing symmetric because here it is quite important. Here it wasn't, because the inner product was real inner product, so it is obviously symmetric, but tensors need not be symmetric. So I will have to write that it is symmetric. Symmetric, positive definite, smooth, covariant two tensor field. So this is for those who are familiar with the tensors. So if you are not familiar with the tensor, you can ignore this thing. There is no problem with that. So we have the Riemannian metric. So if you take your smooth manifold and you endow it with the Riemannian metric G. So now for the sake of simplicity, I will not write this point P every time. Okay. It is when you know the definition, you know that you are assigning this metric to each point. At each point you have your tangent space TPM, and there you are assigning this inner product. You already know it. So it is clear by context. So if you have your smooth manifold and the Riemannian metric, then this is called the Riemannian manifold. But you see, this is just a definition. This is just tells you, oh yeah, so Riemannian metric is just a map from the product of TPM to R. But it doesn't tell anything like how, if we have some space, if we have some smooth manifold, how we are going to find out what the Riemannian metric is. Like what is the explicit formula kind of thing that we can use to actually figure out the Riemannian metric on a smooth manifold. So let's first do that. Let's first try to find out what is the information that it contains. Let's just try to construct some explicit expression. So I will call it the local expression. Local expression for Riemannian metric. So let's do that. Now we know that Riemannian metric is actually defined on TPM. So of course this G will act on some tangent vector, will act on tangent vectors. Now in domain we have the product of TPM. So of course it's going to be act on two tangent vectors, let's say x and y. But still, how we are going to do anything with it? Well, we know that TPM, this is a vector space. this forms a vector space. And if it forms a vector space, of course it has a basis. So whenever we want to do any kind of calculation on manifold, it's a very important thing to keep in mind that whenever you want to do any kind of calculation on manifold, you go local. You look into a chart. So let's say, take the chart U with coordinates x1 to xn. So this is your chart. If you have this chart, then you know the basis vector for the TPM. So basis vector for TPM are these del over del x1 up to and so on del over del xn. So whatever the manifold that I have taken here, dimension, this is a finite dimensional smooth manifold with Riemannian metric defined over it. The dimension of it is n. So this is what we have. This is your chart induced basis. So these are the things that you must have done in your study of a smooth manifold. So this is the chart induced basis for TPM. Now we can do something. Why? How we can do something? If you have two tangent vectors in TPM, what you can do is you can write these two vectors as the linear combination of these basis tangent vectors, right? You can do that. So you can write xi del over del xi. Now, just in case you confuse these xi, let me change it a little bit. I'm going to use capital X. Okay. So I runs from 1 to n, and I can write y as yj del over del xj. So right now I am using the summation symbol, but as we go further along, I will not use this summation symbol. I will introduce the Einstein summation convention, and according to that, we will not require to use this summation symbol everywhere. We can just ignore it. But for now, I'm going to use the summation symbol. There is no problem. So up to here, I hope everything is clear. If you have any two tangent vector, and since you have the basis also, you can write them as the linear combination of the basis vector, and these xi and yj are the components of your basis vector. So let's apply it and see what we get. We have the metric G. It operates on the tangent vector x and y, but we have already written x and y as the summation of these xi del over del xi, I equals to 1 to n, and the y is j equals to 1 to n yj del over del xj. Okay. Now, what this G is? G is actually an inner product, and you know that this is the property of the inner product. You can take the summation out, right? You can take both the summation out. So I'm going to combine both the summation and write it like I comma j equals to 1 to n, and these xi and yj are just the components. And you know the property of the inner product that components can be taken out of the inner product. So I'm going to take them out also, xi, yj. Okay, so these are the properties of the inner product. You can take the summation out and you can take the components out. So what you are left with is this inner product of the basis tangent vectors. So these basis tangent vectors that you have, we denote them this entire thing. We denote it by Gij. So we can write that in a chart what we have got, that G of xy is nothing but summation I comma j equals to 1 to n Gij xi yj, right? That's what we have got. And these Gij's, these are called the metric components. And now we have something which we can use to actually figure out a Riemannian metric on the given smooth manifold. And to determine, but how do we do that? The most important part is to figure out these GIJs. If you have figured out these GIJs, figure out these for a given manifold, then you have figured out the metric. You have figured out the metric. And this is done by obtaining, this is done actually by obtaining a coordinate system. Some coordinate system. So let's say like this map. So if you have done your manifold theory, so there if you are proving given a set, given a topological space is a topological manifold or a smooth manifold, then you need to define the chart map. That chart map provides you a coordinate system. Basically it provides you a parameterization. So if you have the parameterization, basically it provides a parameterization. So if you have the parameterization, then you can figure out these GIJs, because you just need to differentiate with respect to these xi and xj, the coordinates, that whatever the coordinates you have. If you have the Cartesian coordinates x1, x2, xn, if you have some other, you will differentiate according to them, and then you can write it in the compact form and you get the metric. So this is what we have done till now. What we have done is we have taken a smooth manifold and we have defined a tool, a kind of inner product, and this provides you a tool on a manifold to be able to measure length and angles. And then we figure out a local expression for it that allows us to actually calculate the Riemannian metric, the expression for the Riemannian metric. In next video, we will go through the examples of the Riemannian metric. So in next video, we will go through the examples of Riemannian metric, and you will see the first example is going to be the Euclidean space, the very trivial example. And on Euclidean space, I think you can figure out, you can guess that what's going to be the Riemannian metric, because ultimately Riemannian metric is an inner product. So what's going to be, what is the obvious choice, what is the obvious guess that you can make for the Riemannian metric on Euclidean space, while knowing that Riemannian metric is nothing but a kind of inner product? Of course, it's going to be the dot product, the usual inner product that you have on your Euclidean space. So that's what we are going to do. Today was just an introductory video. I hope you understood everything. Thank you very much for watching.